talk is about energy minimizing configurations for Cosserat shells. This is all joint work with my advisor, at Cornell. So here's a quick outline of my presentation. So I'm going to start with motivation for why we're studying these models. We're really motivated by some nice, interesting physics. And then I'll move on to talking about membrane models in particular. What are they? What properties do they need to satisfy, etc. And then we'll also talk about single director Cosserat models, which is in the title, and why these models are appropriate for modeling the kinds of phenomena that we're interested in. I'll state the main theorems and give some quick outlines of so motivation. So really, I think it's best to start with a thought experiment, but this is something you can actually do at home. So take a piece of thin elastic sheet. So what I have in mind is like plastic wrap that you use for food, etc. It should be thin, it should be stretchy, and then clamp them on both sides. So by clamping, I mean they should not be allowed to move in the, like if I hold it like this, the edges should not be allowed to move in the vertical direction. So clamped like that. And then just pull on the sheet, and depending on lots of parameters, you will see the emergence of out-of-plane wrinkles in the middle of the sheet. Now, this might not sound obvious, but the wrinkles will be in the transverse direction. Now, I don't know how helpful that picture was, so I think it's best to just show you a video of someone actually doing the experiment. So as you can see, when they pull on the thing, some wrinkles appear in the middle. So let's do that again. When you pull on it, the wrinkles appear, and then they disappear at a particular level of stretch. So maybe I can display it again if you could catch that. So though they start stretching it, some wrinkles appear in the middle, and then they disappear. So again, stretch, they appear, and they disappear. So this phenomenon has, for some reason, attracted a lot of attention. I think there are several papers about this, some really popular papers, like in Nature, for example, and even one of those papers got the Ig Nobel Prize, not the Nobel Prize, the Ig Nobel Prize. So it's got the attention of a lot of people, including people like my advisor, and so they worked on a couple of different ways to model this. So first of all, I need to mention that to actually capture this kind of behavior, you need a model that accounts for not just curvature-related energies, but also finite, large membranal strains. By membranal, I mean things like stretching, for example. So it should be able to handle large strains in the membranal part. And the issue that we have is that most rigorous existence theorems, or models of that kind, rely on small thickness limits of 3D elasticity, and they're always characterized by small membranal strains. So we need a theory that can account for large membranal strains. So the reason, that's the reason that we rely on these so-called direct shell models. So this is an older theory from early 1900s, late 1800s, but they've been very successful in modeling these kinds of phenomena. Also, I should also mention that these kinds of models that I mentioned, the Cosserat models, etc., are used in commercial codes widely, and so engineers, physicists, they all use these kinds of models very often, and so it's good to have existence theorems. So these are the main reasons we look at. So I haven't talked about what the model exactly is, so we'll get to that. But before that, I want to mention what a membrane model is. So a membrane, when I talk about a membrane, what I mean is a mapping from some bounding domain omega into R3. So omega is some subset of R2. Capital F is the notation I use for these mappings, and then I denote the gradient of small f by capital F, and then the strain tensor by F transpose F and then the membrane energy density is going to be a function of capital F. Okay, so generally these membrane energies are not even rank 1 convex when in practice, like the kinds of membrane energies that people use are not even rank 1 convex. So generically, you don't expect minimizers to exist for these kinds of energies. So here's just an example from a paper by Lee and Healy, where this is the membrane energy they used. They actually used this to predict the wrinkling behavior that I showed on that first in the video. And in fact, they're able to predict the appearance and the disappearance of the wrinkles. And then there's also, I didn't mention this, but the appearance of the wrinkles actually depend on the aspect ratio of the rectangle. So if the aspect ratio is too high or too low, you don't get the wrinkles. And this kind of membrane energy is able to predict this kind of experimental things. So, and yeah, so as you can see, this is dependent on the trace of the strength of C and the determinant of C. It actually blows up when the determinant of C approaches 0, but it's not hard to show that this is not even rank 1 complex when F is a 3/2 matrix.
Determinant of C going to 0, I don't understand. You go to 1, right?
When determinant of C goes to 0,
it's positive definite. So transpose F. Can the determinant of C go to 0? What kind of deformations are you talking about?
Well, anything that would lead to infinite compression would lead to determinant of C going to 0. So if the determinant of C approaches 0, if the local area ratio, for example, goes to 0, then that would lead to determinant of C going to 0. In fact, minimizers in the theory will have determinant of C possibly being 0 on sets of measure 0. Okay, and so I should mention again that the lack of rank 1 convexity usually leads to lack of neural semi-continuity, and that is what leads to this kind of wrinkling behavior. So you can have, you can take minimizing sequences that have these like wrinkling patterns, and then they could have these oscillations at very fine scales, and but that kind of sequence will not actually converge to a minimizer. So that, yes.
Advantage of the fact you're kinetic behavior. Does he give you any intuitions of how he designs these potentials?
Oh, this potential? Yes. So as I've written there, this is based on the Mooney-Rivlin fellow. I'm not sure how that name's pronounced. Materials, but Mooney-Rivlin materials are based on like experiment, from what I understand. Yes.
Is it obvious that the minimum of this is when C is the identity? Or it doesn't have to?
That's a good question. So when F is the identity map, this would go to 0, but is that the minimum? It's not obvious to me. Yeah, I don't have an answer.
Okay, because that, I mean, kind of the basic property.
That would be a desirable property. Yeah. I'm pretty sure they would have ensured that that is true.
Okay.
So, yeah. But that's something I've not thought about. So really, I just want to emphasize that this like lack of rank 1 convexity is very important for predicting this kind of wrinkling behavior. Okay, and so how do you resolve this? Like, so as I said, you can have oscillations at arbitrarily fine frequencies. How do you resolve these wrinkling patterns? Well, you can add on a bending energy. And then the bending energy will penalize the formations of these wrinkles, and then you'll be able to resolve the wavelengths and amplitudes of these wrinkling patterns. So that's the bending energy is where in physics that's what resolves the wrinkling patterns. Okay, so now as I mentioned, we will talk about single director Cosserat models. So this is a very general class of models that account for curvature and membranal effects. So the kind of picture that you should have in mind is you have a really thin sort of domain, and then you apply attractions, boundary conditions, etc., and you get a deformed configuration. But then, although in mind you should be having something that is thin, we just model omega as being a subset of R2, open bounded digits. And then the configuration is defined by two maps. So the first map is F, as I mentioned on the previous slide, which kind of represents these membranal things. It tells you how this set omega sits in R3. So it's like it tells you about how the midplane behaves. Now, but then of course there's some thickness, and we want to model how the thickness behaves. So that's where the second field, which we call the director field, D comes in. So D is also a mapping from omega into R3, but really you should be thinking of it as a vector field sitting on the deformed configuration. So, for example, so as I said, D represents how the thickness behaves. So D can change in length. So when D changes in length, that corresponds to thickness changes. And D can change its angle relative to the tangent plane of the surface. That describes shears, etc. So you can have all these kinds of very general kind of behavior in these. And then I'm also going to write down capital F and capital G, which are the gradients of small f and small d. These are 3x2 matrices, and then I'm going to define these 2x2 subdeterminants of the 6x2 matrix that you get by putting f and g one on top. So, for example, in my notation, M1 is the subdeterminant that I get by picking these these two rows of the 6x2. Then M5, for example, is when I pick this row and this row. And there are 6 choose 2 different ways of doing this. 6 choose 2 is 15. This listed them all out for fun. So we have 15 different subdeterminants. This is not a it's not an illuminating slide, but the reason I wrote it down is because the first 3 of these are more important than the rest in the remaining analysis. Because the first 3 are M1, M2, and M3 are the ones that depend only on F. So when you pick rows coming only from the first 3 rows, you get M1, M2, and M3. M4 to M15 can have these mixed terms between F and G, and then, of course, the last 3 only depend on G. So I want to note that M1, M2, and M3 depend only on F. Okay? All right. Finally, I did say that the director field D has a lot of freedom in what we can do, but we have one constraint, which is the orientation preservation condition. Essentially, with this quantity J, which is a function of D and the gradients of F, which is defined as D dot the partial 1 of F times cross the partial 2 of F, should always be larger than 0. Now, what this essentially says is partial 1f and partial 2f are going to be tangential to the surface. So d dot this being larger than 0 is essentially saying that d should not, well, if d is 0, then this would obviously go to 0. That's one way that this j could go to 0. The other way j could go to 0 is if d lies along the tangent plane. So we don't want either of those things happening. And also, I should note that J is sort of a measure of the local volume, because it's like a scalar triple product of these 3 vectors. So local, in some sense, we don't want the local volume to go to 0. That's what this is saying. Okay, is that clear to everybody? Okay, so let's move on. So how do we define the energy for such a model? Well, the energy density, due to a lot of physics arguments, you can show that it can only depend on x, d, and then the gradients of f and g. So it's a function from that takes in d, f, and g, and outputs some non-negative number. And then also we wanted to satisfy material objectivity or frame indifference. That's what it's interesting. The total energy, of course, is just the integral of that. I also have some loading here, just dead loads. They're just linear functionals will turn out, and they're not super interesting. They'll just handle themselves. Okay, and then of course, to ensure the orientation preservation nature, we're going to require W to blow up as this J quantity, which was d dot partial 1f cross partial 2f approaches 0. So that is the last condition. Okay. All right. So when I kind of started out this project, I just learned like PDEs, calculus of variations, and my advisor told me look into Ball's work, because that's where this was originally done. So Ball in 1976 or 77 showed that polyconvexity leads to weak lowest continuity of the energy, and that's good enough to get existence theorems in 3D elasticity. And then another paper that I kind of read at that time was Ball et al. 1981, where they generalized this notion for more general mappings, where you have higher gradients, multiple mappings, etc. And you can specialize that notion of polyconvexity to single director Cosserat models. And what that says in our context is that there exists a C1 function phi, which takes in D, F, and G, the original arguments, and then those 15 subdeterminants. And then this phi is convex in these arguments. So it's convex in these 17 arguments. Okay? And then if W is equal to phi in this sense, then we say that W is polyconvex.
So you don't need J.
No, it's a very good question. After that. So this is what polyconvexity in Ball is. Okay, and then as I said, you can establish lower semi-continuity. In fact, CLA 2013 takes this assumption and works on the single director Cosserat model, and he gets existence theorems with almost the same assumptions that we made, orientation, preservation, etc., etc. So that has all the details of this minimization. But getting back to the membrane behavior of this kind of a polyconvex energy, so suppose you were to drop dependences on bending in this energy that is polyconvex in the sense that I just wrote on the previous slide. That would mean that you drop all dependencies on the gradients of D and E itself, and what remains then is this membrane energy, W hat, which is a function of F and M1, M2, and M3, which are the three subdeterminants that depend only on F. Okay, so that's what polyconvexity would imply for the membrane energy So this turns out is still polyconvex in the sense of 3 for 3 by 2, which means that you have well-postedness of minimization problem. Now, if you recall my earlier slide, membrane energies should not have that kind of behavior. You don't expect membrane energies to be lower semi-continuous. So there's a sort of issue with the membrane part of this polyconvex stored energy. So one of the effects is that the bending energy, if you add on a bending energy to something that is polyconvex in this sense, it's completely redundant. You don't really need that to establish the existence of minimums. Whereas when we talked about membranes, it was the bending energy that was, resolving wrinkles. So that is one key thing. What this sort of represents is a relaxed version of what we think it represents is sort of a relaxed version of an actual membrane energy. And this kind of goes back to work by Pipkin about tension field models, where he talks about quasi-convexification as like a means to relaxing membrane energies. And in general, in tension field theories, you don't even have, regions of compressive stress are just replaced by regions of zero stress. Whereas in actual experiments, you can have regions of compressive stress. So that would be a bad prediction. And of course, you can't get wrinkling in these kinds of models in the sense of ball carrying over.
So Gokul, one question I have is, so are you saying that if the energy was polyconvex, the wrinkling, you could almost think of it like buckling is also something similar, right?
Yeah.
So I thought these sorts of energies would allow buckling to happen. It's a, I suppose, minimization problem in the sense that Uniqueness is not there. But isn't it true that polyconvex energy functions will allow you to have buckling?
Yeah, polyconvex energy should allow you to have buckling, but I think
So why is that a problem?
well, I think
Related to wrinkling.
I don't have. I think there's a sort of difference between just regular buckling and the wrinkling, right? Because in the wrinkling, in a sense, yeah, you're right that they are. Wrinkling behavior is sort of like when you have this experiment, for example, you're stretching, you're producing some kind of compressive stresses in the middle regions, and that's probably what's resulting in the membrane kind of buckling and producing these wrinkles, maybe. But there's this character of like taking sequences, like of producing oscillations, right, which is not present in buckling, as far as I know. In buckling, you have
they are smooth modes. I mean,
yeah.
they are not rank one. Like
and one like major difference from these papers.
But your pictures look very smooth to me. Those buckles.
That's
Anyway, keep going. I don't want.
Yeah, I did want to mention that like buckling usually it's like a pitchfork bifurcation usually when you have buckling. That's from the bifurcation point of view. But this wrinkling stuff actually is not a pitchfork. It's actually a solar center bifurcation. So that's why you have like the appearance of wrinkles, and then the wrinkles disappear. In buckling, that doesn't happen, right? You keep compressing the it just keeps buckling further and further. The pitchfork just keeps going, but that doesn't happen in wrinkling. So there are some differences between the two, although there are similarities. Okay, so moving on. So we need a new convexity condition for that actually predicts wrinkling, but you can also prove existence theories. So so this kind of comes back to the question that you asked, which is so this is the convexity condition that we propose, which is there exists a C1 function that is now a function of D, F, and G, the original arguments, but J, and then the remaining 12 subdeterminants. So it doesn't depend on M1, so it's not convex in M1, M2, and M3, but it is convex in J instead. So it's a small fix, really. But so this is the new convexity condition. Does anyone have any questions about what that actually says? Okay, so that means we can move on. We can actually establish lower semi-continuity with this slightly weaker notion of it's not polyconvexity, but it's weaker than the usual polyconvexity. So what does the lower semi-continuity result say? It says that if Fk and Dk converge weakly in some subnet space P and Q larger than 1, and then we want the Jk's, the local volume ratios, to converge weakly in L1, and then each of the subdeterminants also for 4 to 15, M1, M2, M3, we don't care about that right now. All those to converge weakly in L1. If you have all of these convergences, then you have lower semi-continuity in this sense. Okay. But now let's go back to the membranal part of this new convexity condition. So the membrane part of this, again, drop dependencies on bending, and then it reduces to this, where phi is now convex in F and J becomes the local area ratio instead of the local volume ratio. So where J is going to be determinant of F transpose F square root. Now, this you can show with a not very complicated argument that in general, this is not even rank 1 convex. So if W equals phi, which is convex in these two arguments, then W in general is not even rank 1 convex. In fact, the example that I showed on like the second slide that Lee and Healy used is it's convex in our sense, and it's not even rank 1 convex. So that actually satisfies this our convexity condition, but it's not convex. It's not even rank 1 convex. For F in 3 by 2. Now, this definition actually does not depend on F being 3 by 2. You can define it for F in 2 by 2 matrices. And this actually is polyconvex. It's not just rank 1 convex, it is polyconvex when you restrict to planar definitions. So if you don't allow things to pop out of plane, it is polyconvex. It's the standard definition. But if you do allow things to pop out of plane, then you get wrinkling. So, if you do allow things to pop out of plane, then you can produce these really fine oscillations that can drive the energy lower and lower. You don't get existence of minimizers. But then you can add on a bending energy. And as I showed in the previous slide, when you have bending energy, it will resolve the wrinkling patterns, and you'll get characteristic wavelengths and characteristic amplitudes for wrinkling. So all of that sounds good for this new convexity condition. And of course, compressive stresses for this are not generally zero, like in the tension field theory, which also is more realistic. Okay, so growth conditions and admissibility. So now I'm just going to talk about how you prove the existence theorem for these kinds of energies. So we need growth conditions. So H1, my first hypothesis, is the convexity condition that I defined on the previous 2 slides ago. The growth conditions, we want P, Q, and R to be larger than 4/3, S bigger than 1, and we have growth conditions in F and G, but also in the sub-determinants M1, M2, all the way up to 15. And for generality, the growth condition in 1, 2, 3 have a different exponent from the 4 to the 15. Now, of course, we also want this function to blow up to infinity as j approaches 0. So these are the 3 hypotheses that we have. This is our admissible set. It's a subset of W1P cross W1Q. All the MLs belong to the appropriate LP spaces, and then 1, 2, 3, 4 to 15, there might be different LP spaces. J needs to belong to L1, and of course J we can only ensure is larger than 0 almost everywhere, just like in the result. And then we apply usually boundary conditions. So the existence theorem is as follows: if A is non-empty and then you don't have the infimum is not 0 on that set, then there exist minimizers. Now, how do you prove the existence theorem? Well, I'll just give you a quick sketch. Many of you have probably been down this road, so I don't know how interesting it is for a lot of people. But the growth conditions imply, plus Poincaré, imply weak convergence in the subleft spaces, Fk and Dk. And then the sub-determinants will converge in Lr or Ls, depending on which ones you're looking at, to some alpha L, which belongs to Lr or Ls. Now, what we need to show is that this alpha L is actually ML star, which is ML evaluated at the limit F star D star. So for that, there's a compensated compactness argument. Essentially, when P and Q are larger than 4/3, these sub-determinants can be interpreted as distributional determinants. In fact, when P and Q are both less than 2, or even if one of them is less than 2, then you exclusively have to define the determinants as distributional determinants. And what is a distributional determinant? Well, it's defined through this formula. This is how the distributional determinant acts on a test function. Anyway, it's well known that these distributional determinants converge distributionally to ML star, which, as I mentioned, is ML at the minimizer. We don't know it's a minimizer yet, but at the limit. And then you combine that with the weak convergence result that we got earlier, and you can conclude that MLK converges to ML star in LR/LS. And then we're left with showing that the J's converge, because we need to show that as well, because the lowest continuity result required that to converge in weakly in L1. So observe that this cross product is M1 plus M2 plus M3, the E1, E2, E3 are the 3 ordinary corrections. And you can use a sorbative embedding for DK, because we know it's converging weakly in W1Q, to an appropriate sorbative embedding, combine that with the weak convergence result for these MLs, and that allows you to conclude that JKs converge weakly in L1 to J star. So each of the JKs is bounded to 0, which means that the limit is going to be larger than or equal to 0 almost everywhere. But then you have a blow-up condition as J equals to 0. So that allows you to conclude that even J star at the limit must be strictly bigger than 0 almost everywhere. So that gives you admissibility. Well, also boundary conditions follow from weak convergence too, which are really hard. So you have admissibility, combine that with the weak low semi-continuity result, that gives you the existence of minimizers. So that concludes the proof of the theorem. So here is just some concluding remarks. Of course, we in the paper we handle more general boundary conditions, usually on part of the boundary, etc. It wasn't particularly important to mention that here. So that can be done. And then constrained versions of this theory are apparently very important to engineers, and they use many different kinds of constrained versions of this theory. So one example is when you don't have thickness changes, one example is when you don't have shears, and then there's also the Kirchhoff-Love theory, which is like both of that combined. We can include these constraints very easily into our minimization scheme and get the business of minimizers. In fact, the Kirchhoff-Love theory, there has been like one existence theorem for the Kirchhoff-Love theory, and our convexity condition, when reduced to the Kirchhoff-Love theory, matches with the convexity condition. And of course, as in the case of bulk nonlinear elasticity, we're not able to ensure that our minimizer is satisfied with the Lagrange equations. We have the same issues that bulk nonlinear elasticity has. So, well, here are all the references. These are the original papers for CLA's paper. This is the paper where I got the video from. They actually do the experiments for all sorts of aspect ratios, so I'd recommend looking at that video. It's pretty nice. It doesn't appear in all aspect ratios. And I can see someone's taking a picture. And so this is the paper that recently got published, and all of these results we talked about, and then these are the papers by where I got the example from, and this is Ginsburg. Thank you.